All right, so I'm looking to solve this Behringer Midas AES50 Cat 5 cable length adventure once and for all. How long can you run it? 100 meters? 75 meters? What did the specs say? What does Midas and Behringer say? What actually works? And what are the tests we can do to clearly determine whether a cable will work? And I'm going to look at this from several angles. We'll look at what the manufacturer recommends. What does the owner's manual say? What actually works? How long of a cable can we actually run of a certain type before it fails? And what kind of safety margin should we use in order to guarantee there will be no issues? And finally, we have the ability to test. I've got a DSX 5000 Fluke that will tell us exactly the parameters of the cable. And we can compare those three different things and come up with an answer that gets rid of all of these opinions that may or may not be correct. So running long distances, if you can run fiber, you can use other formats besides AES50. But AES50 can be extremely convenient because it's right on the back of all the X32, M32 wing, all those Midas and Behringer consoles, all the stage boxes, a single Cat 5 cable run, no adapters, no converting, no dongles. No crap. You just plug and play. It's a wonderful way to go. But unknowns, drops, and pops, things that cut out and ruin your show, are not acceptable. How can we determine whether or not these cables are 100% going to work? Well, we never know 100%, but we can get a very high degree of probability. There's several types of Cat 5e cable. There's shielded, unshielded, there's stranded conductor, solid conductor, and all different thicknesses, and they are not all the same in the measurements. If we look at the manual for an X32, Behringer states that we need Cat 5e cable up to 100 meters. Now, does that mean we have to use Cat 5e cable, or can it be Cat 5e or better? Does that mean all Cat 5e cables work to 100 meters? They had so many problems and so many people having issues with pops and drops, they've released a clarifying document. And let's go ahead and take a look at that. Music Tribe says that the minimum cable standard is Cat 5e shielded. Minimum standard is Cat 5e. That means we can use, by their recommendation or their statement, cables that are higher quality than Cat 5e, like Cat 6, Cat 6a, Cat 7, Cat 8. Maximum length recommended for multi-stranded flexible cable is 75 meters. They're saying that you can only go to 75 meters if you have stranded conductors. Maximum length recommended for single core cable, non-stranded, is 100 meters. Now that's recommended. It's not a hard, fast rule. It's just they're recommending you don't go over 75 meters with stranded and over 100 meters with solid conductor. Then they go on to say that 100 meters is the maximum length a Cat 5e cable should be. That's interesting. We cannot go above 100 meters according to that. Is that true? Can we push it? What about newer cables? We already know that lesser cables shorten the distance, can't better cables expand the distance. But that doesn't mean that all Cat 5e cable will be capable of running 100 meters. To determine the maximum length the SuperMac or HyperMac cable can be, a key parameter to consider is insertion loss. This insertion loss should be no greater than 24 dB at 100 megahertz for the chosen length of cable. Well, that's interesting. Now we have a number, 24 dB of loss at 100 meters. The physical construction of the cable influences the insertion loss. When each signal conductor is made from several thin strands, the insertion loss is greater, so saying stranded will hurt the insertion loss. It's unfortunate because multi-strand conductor is more flexible and easier to coil, and it's, us live people want stranded cable. The data sheet of Cat5e cable should show the insertion loss per 100 meters at 100 megahertz. This way we can determine the maximum theoretical length. Well, this is very useful. The maximum length is 100 times the spec limit divided by the datasheet value. Well, this formula we can use to calculate how far we can use this cable. This is super cool. All right, total length. When considering the total length, patch bays include the adapters and stuff. Great. This is interesting. They say Cat5e can be unscreened or screened. Both are made. So they're just saying both exist. But earlier they said it must be screened. Connections terminating needs to be done with great care. Cable testing. Insertion loss is key to determine the maximum cable length. There are other parameters that need to be met for a cable to be a valid Cat5e cable. The only way to be sure a good cable is to measure its Cat5e performance with a dedicated network cable analyzer, like this one I have here. An example is a Fluke DTX 1800 or DSX 602. This is a DSX 5000, so it's a level above the 602 that they're recommending. So we can actually test the cables and see where they take us and how far we can run. All right, so we now know what the spec is. No more than 24 dB of insertion loss for 100 meters of cable at 100 megahertz. I'm going to latch onto that and use that as our litmus test. And let's switch gears and go to actual testing now that we've covered the recommendations from the manufacturer. What we'll do is we'll start with an unshielded stranded conductor cable. That was the original spec, 100 meters long. I'll plug that in here and here. We should hear music once this gets going. And we're stable. Now we can check this ESD discharge with an electronic lighter here. All right, that's pretty much anywhere I hit this, it shuts it down. This is one of the problems of somebody has carpet or whatever you have that has static electricity, frizzy hair, your PA is muting. But that electronic discharge aside, let's go ahead and extend this out till it fails. So I've got a pile of cables here and I'll use the same extensions for all the different baseline 100 meter cables that I'll be testing. So we're looking to see how long we can extend it before it fails. And this is a 10 meter extension. Seems stable. Next, we'll add in a 16 meter extension instead. That should be this guy down here. Cool. We could listen longer, but we'll do other tests to really ensure the stability of this. And there's a 24 meter cable. So now we're at 124 meters. Cool. And the baseline 100 meters is unshielded. So let's go ahead and add this 16 meter in and go to 140 meters. Okay, 140 meters and we're dead. There's our instability point. And we could try 132 meters and see how we're doing. By knowing these failure points, all right, good enough. But we also have that unshielded cable that's not recommended due to electrostatic discharge. Turns out the shielded cable doesn't go as far because the shielding adds capacitance. Capacitance rolls off high frequencies, and 100 megahertz is the test frequency, or goes up to 100 megahertz. That's a high frequency. The capacitance of the cable acts like a low-pass filter and makes this not work well. The shielding makes it worse. but it also protects us from the sparks. Kind of a trade-off. This is part of the confusion of all this AES50 stuff. Let's go to the actual cable that Behringer makes. This is a Clark Technic 50 meter piece, and 50 meters is a pretty short run, so we shouldn't have any troubles with that. Typically 70 or 80 meters is where this stuff starts messing up, and I'm confident that will work. Let's grab another one of those and go to 100 meters of Clark Behringer cable here. Cool, we got it. Took a second, but how much headroom do we have? How much buffer? How close are we to catastrophe with 100 meters of this cable? Well, let's add it up in small increments. We'll start with the 10 meter chunk. Nice. Oh. Okay. So at 110 meters, this is dropping out. We are quite close to its failure point. Maybe a bit too close. Do we want to trust our show to a cable where adding just 10 meters, just 10% is going to cause a catastrophic failure? All right, let's go ahead and plug this back in 100 meters and check our ESD. And we've got that too. Okay. Let's go to 50 meters and check our ESD. Oh, look at that. Oh, got it there, but 50 meters were pretty good with the ESD. So, the amount of signal we're losing through the 100 meter makes it susceptible to that charge spark. Interesting. All right, let's get rid of these. 100 meters right on the edge of functioning. You know, you get a cable that gets pinched or it gets older or a little dirt in the connector ends, and you've got a show-stopping catastrophe. Let's try a Cat 6 cable. Now, Cat 6 is not as good as Cat 6A, which is rated higher, so we'll give this Cat 6 a try though. And this is a Sommer, I don't remember the model number, but it's a pretty beefy 8mm heavy-duty cable that I was using for testing because I was working on, or I am working on, designing a cable to solve this problem of 100 meter limit. Okay, nice and plugged in. Try the ESD. Stable there. Oh, a little unstable there. Still unstable on the far side. I think that might just be the way of the world. But with the unshielded cable, it was unstable on this side too. All right, let's extend this out and see how far we can go. We'll start with the 10 meter extension. We'll actually know these cables' exact distances or lengths in a bit when we go to the next phase where we use the cable certification meter. Okay, there's 108 or 110. Let's go and swap that with a 16 meter. Good fun. Making messes here, trying to move quick, and happy I'm not doing this at a gig, trying to make something work. I'm doing it so you don't have to do this at a gig. All right. Oh, and we're dead. So now we got a barking dog, and we've got a dead cable. All right. So this Cat 6 cable is not much better than the Clark Technic Cat 5e cable. Seems to be about the same. Interesting. All right, let's go on and test this cable that I've been working on, that I'm trying to not only hit 100 meters, but get something that's stable beyond 100 meters. Now this is a 100-meter piece of Cat 6A cable. So this is a higher quality or a higher bandwidth than the Cat 6. And we'll test that later. Okay, we'll plug that in and see if we got 100 meters here. All right, let's go ahead and check the ESD. That's cool. Let's see if you can see that in the camera. Hopefully you can see it. But that's pretty stable. It seems like it's ESD slightly more stable, but not a definitive test. Let's extend it out and see how far it goes. And we'll start with 110 meter. So far so good. Let's go to 116. Now 124 meters. Let's try 132 with 2 extensions. Let's do 140 meters. Now, there are other Cat 6A cables out there. There's lots of cables, or there are cables out there, I'm sure, that have the capability of going far like this. I'm just showing that this is the one that I'm working on, and it has this capability. And it's also designed to be windable and tour rugged. That's red. Okay. 140 meters. Oh, okay, that's a little surprising. Let's go to 150 meters. Let's see if that works. Ooh. Oh, there it is. Okay. There's our dropout. $150 meters. Okay, 150 meters and it goes unstable. All right, cool, fun. So the next phase or set of tests will be with the actual cable certification tester, and we'll look at the specifications of what we just did and see how that aligns up with the manufacturer's recommendations and parameters. For the next adventure, I'm going to use this DSX 5000 Fluke cable certification tester. I've got it set up for 100 base TX Cat 5e, and I'm using a UTP setup for this, and I've normalized it for these adapters that I'll be using because it does not have ethercons on it. Let's go ahead and test this up. And it passes the test. It's got no shield there. Performance, and we want to worry about insertion loss. The insertion loss is 0.1 dB margin. It is right on the money there. Barely passing, but not failing. And we will see a lot of cables fail in this test. That does not mean they're bad. It just means we're using them at a longer distance than the Cat 5e spec dictates for this cable. We'll go ahead and extend this out till we get to the failure point. Now this one will probably fail because we were so close before. And there's our fail, but that's okay. Our insertion loss is negative 2.2, and let's go ahead and check the next one. And that way we'll have the data on all these various cables And so we'll be able to try and correlate what the data is telling us versus when we saw the actual real world failure. And we hopefully will learn some cool stuff from that. We'll learn what our buffer could be. And there's a failure, and our insertion loss is negative 4.5 dB on the 116. Next we go to 124. All right, and our insertion loss at negative 6.4 dB. Put in 132. Insertion loss negative 8.9 dB. And let's go to 140. And negative 11. And let's get all the way up to 150. And negative 14 dB insertion loss. And the next one we want are the Clarks. So for the Clark cable, first thing we'll do is the 50 meter. Okay, so the 50 meter works. Cool. All right, let's do 100 meters of Clark. All right, there's our 100 meters of Clark cable. And then we're going to put the 8 meter extension in. 8.3 dB of insertion loss. Now we'll go to 16. Negative 10.7. Cat 6. Even though it's Cat 6, we're going to test to the Cat 5 FUTP spec because that's what our manufacturer calls out for. So the cable grade can be higher, but we can still test it to the exact spec that we're looking for. And there we go. And it fails the insertion loss. Let's go ahead and extend it out. And we know this is going to fail. It failed at the shorter distance. And we're at negative 7.4 dB insertion loss. And we'll go one more. I'm not going to go through all of these because this thing failed at the 108 meter length. And negative 9.6 dB insertion loss. All right, now this one made it all the way up to what, 140 meters and crapped out at 150. Well, that's cool. Insertion loss, 4.3. Positive. This is good news. Let's go ahead and extend it out. That passes too. Let's go to 116 meters. I worked on this cable for quite a while to get it to do exactly this and worked with the manufacturer. I don't know all the ins and outs, but I worked specifying it and had this made. There are other cables. I mean, you go out and get really high quality, high bandwidth cables. I'm sure they're out there. I know they're out there. But they weren't windable. They were like too thick or they solid conductor. Getting a stranded conductor, coilable, heavy duty tour grade cable is a challenge. And we failed that test. We have an insertion loss of negative 0.7. Pretty close though to what we would want. 124 meters. And we have an insertion loss of negative 3.3. Let's go to 132 meters. And finally, we're going to go to 150 meters. Cool. And I'm going to do one more test. This cable that I have here is a lower grade than the red cable. And I have a 10 meter piece of the red cable. Let's see what our spec is with 10 meter extension of this. It failed on length, but not insertion loss. That's kind of interesting and exciting because insertion loss is what we care about. We know it's too long. Now here's the key. Can we get to 120 meters and be within spec on insertion loss? We know it's going to fail length. Oh, insertion loss was so close. We're at 0.4 dB, almost in spec. If we had all red cable, maybe we would be in spec, and we'll be able to calculate that out. All right, well, that completes the testing part. Next adventure will be data analysis, and we'll look at what the units measured and what the real world failures were and correlate those and come up with some understanding if all goes well. I've got the 4 100 meter tests, the Unshielded, the Clark, the Cat 6, and the Super Cat XM. And in this window, we can look at the insertion loss and see it's 23.9 for the Unshielded. We can look at a graph of that as we looked at before. And then this information over here tells us the margin, so that if we're 0.1 dB off in the positive direction, that means we're 0.1 dB off of the 24 dB at 1 meg limit there, or 0.1 dB off of the red line, and it might be at a different frequency. And we can see that in here. Cool, and there's the limit of 24 dB. And next is the amount of crosstalk, and return loss is how much energy is bouncing back from the other end, and we want more loss there. We don't want a lot of energy going from one end of the cable to the other and then coming back the other way. Length is the length of the cable. Propagation delay is how long it takes the energy to travel from one end to the other. Delay skew, that's the difference between the time of the various twists. So we want that to be low. We don't want a big differential. If the twists are twisted at different rates, which helps reduce the crosstalk, it increases the skew. And the resistance is just the DC resistance. Impedance is the impedance of the cable. We're looking for 100 ohms in and about. And the wire map passes. That just means if we're testing for unshielded, we see that it's unshielded and all 8 wires are there, and we see the shield on the shielded ones. All right, so let's go ahead and we look at the graph that we saw before. Paired data. Next, we can look at the crosstalk energy and then what our goal is. Return loss, same thing, worst values, and there's some other stuff we can see here. So let's go ahead and go through this looking mainly at what we care about. Here's the unshielded at 23.9. We can call up a calculator here, and we saw that formula before, and we say 24 divided by 23.9 equals times 100 equals. That means that we can run this cable 100.4 meters according to the specification provided by the manufacturer. That unshielded cable is right on the money. All right, so let's go ahead and look at the next one. Here's the Clark Technic, and we'll poke around a bit. Here's the insertion loss of negative 5.9, which means we're over that 24 dB maximum. We see 29.8. 24 divided by 29.8 equals times 100 equals. All right, so this Clark cable is good, according to the manufacturer, up to 80.54 meters. And let's go on to the next one, the Cat 6. Insertion loss, negative 5.6. The next at 14. Now the next has gotten better because we have individually shielded pairs instead of an overall shield. Return loss is borderline, or we can see our propagation delay is 531 and our skew is 19, 29.6. Let's calc that out. 24 divided by 29.6 equals times 100 equals 81 meters. Not much different than the Clark cable. Finally, let's go to the SuperCat XM. Here we've got 19.7 for our insertion loss. We can look at this. We've got our next is 18.9. So we've really got excellent crosstalk spec. The return loss, we want that to be a high number. Propagation delay, 460, which is quite good, as well as the delay skew at 13. Look at this value for insertion loss. Let's go ahead and calculate that. 24 divided by 19.7 equals times 100 equals 121.8 meters. So we can run this cable according to the manufacturer's specification almost 122 meters. Very interesting. So now that we've tested the 4 different types of cables and we know how long each can be before it fails, let's take a look at the insertion loss of those failure lengths and see if we can find an actual number that relates to the failure. So the unshielded cable at 132 meters has a 32.4 dB insertion loss. The CATe, 108 meters, has got a 32.1. The Cat 6 at 116 meters is 33.4, and the SuperCat XM at 148 meters failed at 33.7. Now that's super interesting. We're seeing that they are within 2 dB of each other. The AES50 does not seem to work. It goes unstable somewhere around 32 dB of insertion loss. Super handy to know. Now that we've got that, let's try and reverse engineer a safety margin so that we can easily calc the safe working distance by extension testing. So out in the field, you can keep extending the cable until it fails, and then multiply it times a number and know the safe working distance. You won't need the tester, and you can do it super easily. All right, so let's calc out our safe working distance multiplier. So what we're going to do is look at the longest working length for each of the cables. And I've taken them here. The unshielded cable failed at 132, so I selected the 124. The CATe failed at 108, so I selected 100. The Cat6 failed at 116, so I selected 108. And the Super Cat XM failed at 148, so I selected 140. These are cables that test and work. The longest working length. Then what we're going to do is figure out the multiplier. Well, they seem to fail at about 32 dB, and we know that the manufacturer's spec is 24 dB. If we take 24 divided by 32, we get 0.75 or 75%. So that tells us that we should be able to multiply the longest working length times 75%. And this one here at 124 meters, 124 times 0.75 equals 93 meters. And for the unshielded cable, the tester told us that we had 101 meters of usable length, so that got us within 8 meters. A little conservative, but that works. Let's do the Clark. And it says 100 meters. We know that without calcing, but we'll do it anyways. 100.75, and that's 75 meters. And I believe it was 80 meters. And the 108 here, 108 times 0.75, I believe this was 81 meters, and it's dead on. For the Super Cat XM, 140 times 0.75 equals 105 meters. So that's a super simple way to test in the field any cable and know if your show is safe and not find out the hard way when the show goes down to silence or sonic booms. 75% of the longest working length will give you your safe operational length that parallels what the very expensive tester and the manufacturer's spec tells us. So we looked at how long of a Cat 5e cable we can run with music and a bunch of channels running down AES50 before it fails. And we found those failure points for an unshielded Cat 5e, a shielded Cat 5e, a Cat 6, and a Cat 6a cable. Then we looked at it from another angle, and we took the DSX 5000 Fluke cable certification tester and actually measured those cables, used the manufacturer's formula, and calculated out what they say would be the maximum cable run for each of those, and then took a look at the actual measurements from the cable analyzer versus the specification, came up with a multiplier of 75%, multiplied that times the longest functioning cable length that worked with music to come up with a safety margin. We don't want to run these cables at the last possible length and have them on the verge of failing. We need a buffer. We needed to know what that buffer was, and we were able to calculate what I believe to be a reasonable and reliable safety margin that we can depend on. One that parallels and is in line with the manufacturer's spec and actually is even more conservative. So let me know any questions that you have, and hopefully this info is helpful and we can put AES50 cable failures to rest once and for all. We can use higher grade cables. We can calculate or very easily determine whether the cable will be reliable, and the Super Cat XM cable will be available soon. if you need cable runs exceeding 100 meters. And I believe that once we get fully SuperCat XM cable with SuperCat XM extensions, that 120 meter will be within the manufacturer's spec. All right, let me know what you think, and cool.